Well, good evening. How are you? How's it going? Hope you're doing well. We're going to start off with part 2 of the acid-base chapter. And part 2 will be mainly about salts, the properties, and the pH of salts which have neutral salts, acidic, basic, or amphoteric salts, and those salts which look like amphoteric salts, which are made of weak acids and weak bases. As well, in part 2.2, we're going to look at the polyprotic acids and the calculation of the pH of polyprotic acids and polyprotic bases. And in part 2, we're going to start off with mixtures. The first part, we're going to do mixtures of acids, then mixtures of bases, and then we're going to do a specific type of mixture forming a buffer, which is a mixture of a weak acid and a salt, or a weak base and a salt. That's the outline for part 2, which will be taking around 4 recordings or so with the problem sets. Okay. We're going to start right off with the definition of a salt. So a salt is actually an ionic compound, and it's always in a solid form outside the solution. Once it's inside the solution, the solid dissociates into ions, anions, and cations. Now the salt may come from a solid and a compound, and you may just buy it and from the solid compound. Or this salt may come from the reaction of an acid-base neutralization reaction, but then it's already in solution, and so it's already in its ionic form, and then the pH is not really considered through that type of reaction. So the salts that we're really looking at are real solid salts that we put in solution, and we're going to look at their pH, okay? And we're going to see how these salts affect the pH of pure water, okay? So we're looking at the effect on the pH of water. The first type of salt is a neutral salt. And in the neutral salt, both the cation and the anion are spectator ions. And if you remember, the cations that are spectator ions are the ones that come from the same cations that come from a strong base, so such as sodium, potassium, calcium, the group 1A and 2A elements. And the anions, which are spectators, are those anions, the conjugates of the strong acids, such as Cl, Br, NO3, ClO4-, but not the H2SO4. And this is pretty much why, actually, I got you to memorize the strong acids, knowing that you're going to really need them when you get to the salts. Because once I know the strong acids, I know their conjugates, so it's easy for me to know if the anion is reactive or not reactive. So in the case, for example, of NaCl solid, when I put him in water, of course, he's going to split into Na plus and Cl minus. Both Na plus is a spectator, you all already know that, and now Cl minus is a spectator because it's the conjugate of a strong acid, which is thus a spectator ion. And if neither one reacts with water or is reactive, and therefore we only have water in solution contributing to the pH, and my pH will be 7. In the case of basic salts, however, the basic salt, when he's split up into a cation and an anion, the cation is actually the conjugate of a weak acid, okay? It's a weak acid, and it's the conjugate of a weak base. In other words, the cation in this case is reactive. So look at him, ammonium. Of course, if I put ammonium, it's not a spectator ion. Cl minus, he is a spectator ion. And in this case, the cation can react with water. How does he react with water? Well, when you put this ammonium cation in water, he acts as an acid. He will give a proton to the water. he becomes ammonia. And so this is now called an acidic salt. Why? Because one of its cation is able to react with water to give me H3O+. And so in solution, I now have more H3O+ coming from this salt upon dissociation. So how do I calculate the pH of such a solution? Well, the pH of such a solution is just the pH of a weak acid. It's as if I have a weak acid in solution. And this is why I really like to do salts right after we just discussed the pH of weak acids and weak bases, because the calculation of a pH of a salt is exactly the same. So this will act as a weak acid, and therefore if the concentration is greater than 100 Ka, you use pH equals half pKa minus half log C. But if the concentration is less than that, you will use the quadratic, which comes from the Ka expression. And where's the Ka expression? Oh, it's just the reaction with water. And of course, you can expand this and you can put it in the H3O plus form if you really want to, if you've memorized it that way. And we are done. Here, the X is simply H3O plus, and you get the pH. Very easy to do the calculations of such. What about basic salts? Well, basic salts have an alkali metal as the cation, but the conjugate, the anion is the conjugate of a weak acid. Looking at this example, ammonium acetate. So here my cation is a spectator. What about the acetate? Well, will this anion react with water? Yes, it will. Why? Because this anion is not an anion of a strong acid. It's an anion of a weak acid. And therefore, yes, it will react with water. It's a reactive anion. This anion will then react with water, and it will react as what? As a base. It's an anion and it reacts as a base. It will pick up a proton from water, thus producing OH minus in solution. So my pH here of water will be more basic because we have OH ions produced. What is the exact calculation? Well, guess what? We will simply use the calculation of a weak base solution because this anion acts as a weak base. And the concentration then, if it's greater than 100 kb, remember with base solution we think of kb, then we use either one of these equations, POH is half pKb minus half log C, and then get the pH value, or pH is simply 7 plus half pKa plus half log C. This is why, guys, I told you, please study the first parts, because from here on, we're always going to use these equations. Wait till we get to titrations. We're going to simply use them. If the concentration is less than 100 kb, then we use the quadratic equation, which comes from the kb expression, which of course we can use the equation for it. We have acetic acid, OH minus, divided by the acetate ion, this minus on the bottom, or simply x squared, C minus x, the initial concentration in solution minus the x. And what is this x? Don't forget this x is OH minus concentration. It's simply a basic solution. It's as if I never had a salt. The idea of a salt, you know, is just extra. Now this is a little bit different, so I have to gear you up. This is an ampholyte, an ampholytic salt. So first let's talk about what's an ampholyte. Okay, an ampholyte is a substance that can act as either an acid or a base. And of course you already know that water is an ampholyte, right? So that's one example. He can act as either an acid or a base. But here we're talking about something different. These are salts such as sodium hydrogen carbonate. So let's look at this. This is a salt, solid. In water, of course, in water, he will split to become Na+, which you all know now is a spectator, and HCO3-. Now I call this an amphoteric substance. The idea is that this substance can act as either an acid or a base. Look at him. He has a negative charge, and thus he can pick up a proton from the water. Thus, he's acting as a base. Okay, and then we get OH minus in solution. And he has a hydrogen, which is slightly acidic. So he still has an H, which can be donated to water. And so this HCl CO3 minus has an H, which can be donated to water, becoming CO3 minus and H3O plus. Well, a little bit later on, we're going to talk about these diprotic acids. But now I want you to see this as some material that has a negative charge and that has an H. Okay? And if it has a negative charge and it has an H that can be donated, then this is an amphoteric substance. Now, how do we calculate the pH of this ampholyte? Well, the first equation, I need a Kb. The second equation, I need a Ka. And it turns out that, you know, the actual how do we do this and where do we get the pH is not so easy to derive, but I will derive it for you. I will derive ampholytic solution pH once I see you in class, but I'm not going to do it here on the board or in the recordings. I will simply say that the pH will be the half pK first dissociation of the acid and pKa2 the second dissociation of the acid. Okay, this is for this type of ampholyte, which is of the form Ha1. Okay, Ha minus, sorry. So this comes typically from diacids. Removing one proton, you can also get Ha minus. And the pH of this Ha minus in solution and this Ha minus in solution acts as an ampholyte. One moment it can react with the water to give OH minus, one moment here reacts with water to give H3O plus. And thus I want you to memorize that the pH of such ampholytes is simply half pKa1 plus pKa2, where here the Ka1 and the Ka2 is the first dissociation of the acid and the Ka2 is the second dissociation of the acid, which we're going to look at when we get to diprotics later. Another type of salt, which also, when he splits up, will give me a cation, which is reactive with water, and an anion, which is reactive with water, and that both together will act as an ampholyte, and I will show you why. Let's look at this example. Acetate and ammonium acetate in water, solid. He splits, he becomes aqueous, and he starts to split up into ammonium, and we all know that ammonium can react with water because he's not a spectator ion. And into the acetate, and we all know that this anion can react with water because he's not the conjugate of a strong acid. So let's look at each of those reactions separately. The acetate, when he reacts with water, he reacts as a base. So he's going to pick up a proton from water, giving me OH minus. The ammonium, when he reacts with water, he reacts as an acid. He gives a proton to water to become H3O plus. The water. Now, if you look at both of these equations, one equation is giving me OH minus, the other equation is giving me H3O plus. Wait a minute, that's kind of like an ampholytic solution. One time giving me OH minus, one time giving me H3O plus. And indeed, this acts as an ampholyte. Now, I can calculate the exact pH, and I'm going to show you the equation, but we can also get an idea about the acidity or basicity of the solution qualitatively, I mean, without knowing the exact pH. So for example, in this case, if my Kb is greater than my Ka, then I get more OH minus ions than H3O plus ions, and therefore I get a basic solution. If my Ka is greater than my Kb, then I get more H3O plus ions than OH minus, then I get an acidic solution. And if Kb is approximately equal to Ka, then I have more or less a neutral or close to neutral solution. Well, great. I can tell if something is acidic or basic, but what is the exact pH? To get the exact pH, you would say that I will use the equation for ampholyte, which is the pH equals half pKa1 plus pKa2. Of course, this assumes kind of a few assumptions that, first of all, that the concentration of the anion and the cation is the same. And of course, in this case, they are because they come from the same salt. So this is 1 to 1 molar and their concentration is the same. And that the Ka is very close to the Kb, such that I can do these estimations. Which is the category that we're going to give you, that you are responsible for. Okay, I'm going to show you an example where that is not the case, but not in this type of an ampholyte. That's when it comes like a mixture of a weak acid, weak base, separately. So here is the derivation for those of you who really want to read it. It's again looking at all three equations, going into electroneutrality, conservation of elements, and acidity constants, and deriving the pH equals half pKa1 plus pKa2. And this here, pKa1 and pKa2 is for the Ka of the one of the couples and the Ka of the second couple. Okay, because these are two different couples for two salts. This is not for the ampholyte solution. And again, like I said, I will go through this derivation for you, but for now, I just want you to use it. Whenever you have a salt, pKa1 plus pKa2 half. There's also another equation, which is here in yellow, okay? In this case, we're assuming that the anion, the bases, and the acids concentration eventually cancels out, okay, in solution. If they don't, then we have to do a bigger derivation and a bigger equation like this. And I'm gonna as well go through the derivation as we solve a problem, and not just like this, okay? So when we solve a problem, I will go through the exact derivation of this, but keep this yellow guy in mind. And that's it for salts. If I have amphoteric salts, you simply say pH equals half pKa1 plus pKa2. Also, for amphoteric salts that come from a reaction of a weak acid plus a weak base, where the acid and the base concentration are not necessarily the same. Okay, if they're not the same, if they were, then they pretty much cancel out. And if Ka equals Kb, everything cancels out, and you can simply use this equation. But if the anion and the cation are not the same, and if the Ka is not really close to the Kb value, then the concentrations of the bases and the acids don't actually cancel out. And we have to actually use this equation, which is pH half pKa1 plus pKa2 plus half log of whatever bases I have divided by the acid concentration, the acids. Acidic salt, we simply use the equation for a weak acid, and basic salts, we use the equations for a weak base, which you are all. You just have to do the either concentration greater than 100 or less than 100, and you either use a quadratic or you use the half pKa1 plus pKa2 for acids, or POH half pKb minus half log C. Okay, right away, after you hear this recording, right away, go ahead and start the problem set, which is number 2, number 26, and number 28. And I will be solving it for you and finishing that part.